90 years. That is how long humanity has been searching for something that makes up most of the matter in the entire universe, something that holds galaxies together, shapes the cosmic web, and controls the very structure of everything that exists, yet cannot be seen, touched, or detected by any conventional instrument ever built. 90 years of searching. And in November 2025, a single researcher sitting in Tokyo looked at 15 years of telescope data and said those words that scientists almost never allow themselves to say out loud. We may have finally seen it. The substance in question is dark matter. And if the finding from Professor Tomonori Totani of the University of Tokyo holds up, it would represent the single most significant discovery in the history of modern physics. Not an exaggeration. The detection of dark matter would reshape our understanding of what matter is, what the universe is made of, and where physics itself needs to go next. This is the story of what was found, how it was found, why it matters, and why the scientific world is not yet ready to call it confirmed. To understand why this discovery is so potentially enormous, you first need to understand what dark matter actually is, or more precisely, what we know it is not, because that is really all we can say for certain. Dark matter is invisible. It does not emit light. It does not absorb light. It does not reflect light. Every instrument ever built that detects electromagnetic radiation, every telescope, every camera, every radio dish pointed at the sky, is completely blind to dark matter. It passes through ordinary matter with almost no interaction at all. Billions of dark matter particles are passing through your body right now, at this very second, and you will never feel a single one of them. And yet we know dark matter is real, because of what it does to the things we can see. The story starts in 1933, when Swiss astronomer Fritz Zwicky was studying a massive cluster of galaxies called the Coma Cluster. He measured how fast the individual galaxies inside the cluster were moving. And the numbers were completely wrong. The galaxies were moving so fast that they should have flown apart billions of years ago. The visible mass of all the stars and gas in those galaxies was nowhere near enough to provide the gravitational force needed to hold the cluster together. Something invisible, something massive, something generating enormous gravity had to be keeping those galaxies bound to each other. Zwicky called it dark matter, Dunkel Materie in German, and the scientific community largely ignored him for decades. Then, in the 1970s, astronomer Vera Rubin and her colleague Kent Ford made another discovery that could not be explained away. They were studying the rotation of spiral galaxies, including galaxies like our own Milky Way. In a normal galaxy, if most of the mass is concentrated at the center, the stars at the outer edges should orbit much more slowly, just as the outer planets in our solar system orbit much more slowly than Mercury. But that is not what Rubin found. The outer edges of galaxies were spinning at almost the same speed as their centers. The only way to explain this was if there was a massive invisible halo of matter surrounding every galaxy, adding extra gravitational pull to the outer regions that the visible stars alone could not provide. This invisible halo was dark matter, and its gravitational fingerprints were absolutely everywhere scientists looked. Since Rubin's work, the evidence for dark matter has piled up from dozens of independent directions. The way galaxy clusters bend light through gravitational lensing reveals far more mass than the visible matter could account for. The pattern of the cosmic microwave background radiation, the faint afterglow of the Big Bang, shows a universe that required dark matter to form the structures we see today. Computer simulations of how the universe evolved from a smooth, hot soup of energy into the complex web of galaxies and filaments we see now only work when dark matter is included. Take dark matter out of the models, and the universe you get looks nothing like the one we actually live in. The evidence is overwhelming and comes from completely independent sources. Dark matter is real, but what it actually is, what particle or particles make it up, has remained completely unknown. The leading candidate for decades has been a class of hypothetical particles called WIMPs, which stands for weakly interacting massive particles. The theory behind WIMPs is elegant. These particles are thought to be heavier than protons, significantly heavier, but interact with ordinary matter and with light through only the weak nuclear force and gravity, which is why they are invisible and nearly impossible to detect. The important detail about WIMPs is what happens when two of them meet. Theory predicts that when a WIMP and its antiparticle counterpart collide, they annihilate each other in an explosion of energy. And one of the byproducts of that annihilation is gamma rays, extremely high energy photons, the most energetic form of light in the entire electromagnetic spectrum. This prediction is critical because it gives scientists a specific, testable signature to search for. If WIMPs are real and they are concentrated somewhere in space, that place should be glowing faintly in gamma rays at a very specific energy level, forming a very specific pattern that no ordinary astrophysical process could replicate. The best place to look for this signal is the center of the Milky Way galaxy. Dark matter, according to our models, should be densest at the core of every galaxy, clumped into a massive halo that gets more concentrated toward the center. If WIMP annihilation is happening anywhere, it should be happening most intensely in the direction of our galactic core. For years, scientists have been pointing gamma-ray telescopes at that region of the sky and sifting through the data, looking for that telltale excess. The problem is that the galactic center is an incredibly messy, crowded, energetically chaotic region of space. Supernovae are exploding. Pulsars are spinning and emitting gamma rays. Cosmic rays are slamming into interstellar gas and generating gamma radiation. The galactic center is a blinding wall of gamma ray noise, and trying to pick out a faint dark matter signal from all of that background is one of the hardest data analysis challenges in all of astrophysics. This is where Professor Tomonori Totani comes in, using data collected over 15 years by NASA's Fermi Gamma Ray Space Telescope. Totani took a different approach to the analysis. He focused specifically on the gamma ray emission above and below the main disk of the Milky Way, the region of the galactic halo, rather than the densely packed galactic plane itself, which he excluded from his analysis to avoid the worst of the background interference. After carefully modeling and subtracting all the known sources of gamma radiation, he found something left over, a residual component that should not be there. A halo-like glow of gamma rays spreading outward from the direction of the galactic center, peaking sharply at an energy of exactly 20 giga-electron-volts, 20 billion electron volts, and then falling away. That precise energy peak matches almost perfectly the theoretical prediction for WIMP annihilation, and the mass of the WIMP implied by that energy level, approximately 500 times the mass of a proton, falls squarely within the range that theoretical physicists have been predicting for decades. The shape of the signal is as important as the energy level. The gamma ray glow Totani detected spreads outward from the galactic center in a pattern that closely matches the expected distribution of the dark matter halo, denser near the core, fading at the edges. This is not a random spike. It is a structured, spatially extended signal with a specific energy profile and a specific spatial distribution, both of which match the dark matter prediction with striking precision. Totani examined the data meticulously over many months. He told BBC Science Focus that when he first noticed what appeared to be the signal, he was skeptical, but the more carefully he checked it, the more it held up. And when he felt confident that what he was seeing was real, he said he got goosebumps. The finding was published on November 25th, 2025, in the peer-reviewed Journal of Cosmology and Astroparticle Physics. The paper was a single-author study, meaning Totani conducted and wrote the entire analysis alone, which is somewhat unusual for a claim of this magnitude. In it, he states directly, if this is correct, it would mark the first time humanity has seen dark matter. He also notes that the dark matter particle implied by the signal would be a new particle entirely, one not included in the current standard model of particle physics. This would mean not only the detection of dark matter, but the confirmation of physics beyond the standard model, a discovery that would reshape two of the most fundamental pillars of modern science at once. Now, before you let the excitement fully take over, it is essential to understand where the scientific community actually stands on this finding. The honest answer is that most scientists are not yet convinced. The skepticism is loud, credible, and based on solid reasoning. Stacy McGaugh, an expert in galaxy dynamics and dark matter at Case Western Reserve University, pointed out bluntly that this is far from a new claim. A similar excess of gamma rays from the direction of the galactic center was first reported as early as 2009. Over the 16 years since then, numerous research teams have studied the same Fermi data and failed to find strong, unambiguous evidence connecting that excess to dark matter. Each time the excitement built up, it eventually faded as alternative explanations emerged or the analysis did not survive independent replication. McGaugh put it plainly, it turned out to be wrong then, and he expects it is wrong now. Jan Conrad, a professor of astroparticle physics at Stockholm University and a leading expert in gamma-ray searches for dark matter, urged similar caution. He told BBC Science Focus that it is notoriously difficult to make these kinds of claims using Fermi data. One of the key criticisms of Totani's analysis concerns the way he modeled the distribution of dark matter in the Milky Way. Rather than using direct observational measurements of how dark matter is distributed in our galaxy, Totani used data from a simulation. McGaugh and others note that real universe measurements of dark matter density tend to be significantly lower than what simulations predict. If the actual dark matter density in our galaxy is lower than Totani assumed, the expected gamma-ray signal would be weaker, and the apparent match between the signal and the dark matter prediction would break down. These are serious methodological concerns. They do not prove the finding is wrong, but they mean that independent verification is absolutely necessary before any celebration is warranted. Totani himself acknowledges this clearly. He has said that if the radiation truly, originates from dark matter. Its scientific impact would be so immense that many researchers would proceed with caution, and he looks forward to other teams independently analyzing and confirming the results. One of the most powerful ways to test the claim would be to look for the same 20 giga-electron-volt gamma-ray signature in small dwarf galaxies that orbit the Milky Way. Dwarf galaxies contain very few stars and very little gas, which means there are far fewer confounding sources of gamma radiation to muddy the signal. If the same energy signature appears in those environments, it would be a much cleaner, much more convincing case for dark matter annihilation. The next generation Cherenkov Telescope Array Observatory, currently under construction, will dramatically increase sensitivity to high-energy gamma rays when it comes online in the coming years. Underground dark matter detectors scattered around the world, designed to directly catch WIMPs passing through shielded chambers buried deep below the Earth's surface, are also continuing to accumulate data. If a WIMP with a mass of approximately 500 proton masses is responsible for Totani's signal, those underground detectors should eventually see it too. And if both the gamma-ray observation and an underground direct detection point to a particle of the same mass and interaction strength, that would constitute a verification so powerful that even the most cautious skeptics would have to accept it. This is how science works. A bold claim is made. The community examines it carefully and critically. Alternative explanations are tested. Independent analyses are performed. The tools get sharper. The data accumulates. And eventually, the truth emerges, either as a confirmed discovery that rewrites the textbooks, or as a reminder that the universe is not yet ready to give up its deepest secret. Either outcome advances human knowledge. Either outcome is valuable. But if Totani is right, if that glowing halo of 20 giga-electron-volt gamma rays spreading outward from the heart of the Milky Way is truly the annihilation signal of particles we have been hunting for 90 years, then we are living through one of the most important moments in the history of science. The invisible universe is not invisible forever. It simply required patience, precision, and one researcher in Tokyo willing to look at 15 years of data one more time and ask a question nobody had fully answered yet. It is also worth pausing to appreciate the sheer ambition of what dark matter detection would mean for particle physics itself. The standard model of particle physics is one of the most successful theoretical frameworks in the history of science. It describes every known fundamental particle and every known force except gravity with extraordinary precision. It has been tested in particle accelerators around the world and confirmed again and again for over 50 years. But the standard model has a glaring problem. It has absolutely no room for dark matter. None of the particles it describes could be the dark matter we know exists. If Totani's WIMP signal is real, it would mean there is a particle with a mass of approximately 500 proton masses sitting completely outside the standard model, invisible to all our detectors, and more abundant in the universe than all the ordinary. Matter that stars, planets, and living beings are made of. This would not be a minor revision. It would be the discovery of an entirely new category of matter, the opening of a new chapter in fundamental physics, and the beginning of what would surely be decades of new research into what the universe is actually made of. The hunt is not over. In many ways, it is just beginning.